way back from 1998. Now I just want to show you briefly why they exclude 1. If n were equal to 1, n squared, the numbers between n squared and n plus 1 squared would just be, let me just write it out. You'd have 1 squared, right? Then we have 2, 3 are the only numbers between 1 and 2 squared, right? I mean, between 1 squared and 2 squared, right? So you see, we're looking for 3 distinct integers, right? So 1 just wouldn't supply. This would be 1, 2 distinct integers. So we need to start with 2. And also just some clarity on this statement. This says C divides the quantity a squared plus b squared. Another way of stating that is to write down a squared plus b squared over C. Just a good old-fashioned horizontal bar fraction here. Okay, is equal to m. All right, where m is some positive integer, and I'll put m, a proud member of z plus. You know, z plus just stands for all the positive counting numbers. Okay, all the positive integers. All right. Now, so let's take a look at the case n equals 2. It's the smallest one that's manageable. And you can quickly see that the hypothesis works out, right? If you choose 6 and 7, which are between 2 squared and 3 squared, you get 6 squared plus 7 squared divided by 5 is 17. Okay, that's easy to compute. So we can see that it holds for n equals 2. Now, we use that special case to generalize here. If we take a to be n squared plus 2, that would give you the 6 you see right here in the case n equals 2. If we take b to be n squared plus n plus 1, that would give you the 7 that you see right here. And of course, 2 squared plus 1 would be the 5 that you see here. So this is an attempt, may not be the only attempt, but let's let the algebra we'll discover proves that it all works out nicely. So this, I won't go through all that. I expanded this out. I expanded a, I expanded b, squared both of them, got this collected like terms. And then from here to here, folks, I left out a long division. I did a long division step. You don't think you want to watch me do long division, but if you do long division, you get a remainder of 0, and you get that as this is your quotient. So again, if you set up a long division problem, you would get to this in about a minute or 2, maybe less. All right. Now, so this does prove everything because this is a member of Z plus, right? By closure, this would be a member of Z plus, and so we've actually shown that it always holds for an arbitrary n. Okay. Again, this idea here is member of Z plus. Since we don't have a remainder, I mean, this is a member of Z plus always, right? Okay. So now. Let's just take a look at one more example. I did it for an easy case, n equals 2. Let's try it out for n equals 3. For n equals 3, let's see, n equals 3. We don't even have to list the numbers, really. We can. These numbers, by the way, are all less than n plus 1 squared. I didn't write that down, but all of these numbers are clearly less than n plus 1 squared. So for n equals 3 right here, we would get what? 11. For n equals 3 right here, we would get 9 plus 3, that plus 1 is 13, right? And then this is equal to what? 10. I guess if you put 3 right there, 9 plus 1 is 10. So what we get right here, let me double check. Oh, y'all, this is 12. I'm sorry. This is 12. No, it's not. No. 3 squared plus 2 is 9 plus 2 is 11. Now right here, 9 plus 3 plus 1. So right here we're getting, now we have to square those, right? Remember, we have to show that C divides a squared plus b squared. So let's write that down. Do we have room here? Yes, we do. So this would be, let me just write this so I'll keep everything straight. A squared plus b squared. Okay, all over C, we want that to be an integer. Okay, so this would be equal to 121 11 squared is 121. 13 squared is 169, right? Divided by 10. And y'all, this is equal to 121 and 169 is 290, so this does equal to 29. So again, we see it works in a couple of cases, 2 and 3, and also algebraically, we're absolutely certain it works. So anyway, I guess we were done. We were done right here. We were done right here at this stage once we got the integer here. So, but this is just a special case that gives you a little more confidence that there's no mistakes made with the algebra. Go Alcaraz.